Good day. In this video, I'm going to discuss the convergence of the given sequence. Now, when can we say that the sequence is convergent or not? In this case, we will use the concept of limit of a sequence. So now, let's consider this definition. If the limit of a sequence exists, the sequence is called convergent. Otherwise, it is called divergent. So, we're done discussing the concept of the limit of sequence. So, if the limit exists, if there is a limit of the sequence, we can say that the sequence is convergent. Otherwise, it is called divergent. Let's note here that a sequence can converge to only one limit. That is, if a limit exists, then it must be unique. Now, let's try to see the proof of theorem 3.5.11 in this lecture note. So we have here the theorem that states that if the limit of a function or a sequence defined as a function exists, then it must be unique. So let's try to consider two limits of the given sequence. So here, we let L1 be the first limit, L2 be the second limit. So our goal here is to show that the limit is unique. So it means our goal is to show that L1 is equal to L2. They are just equal. So by definition of limit, we have this one. So if this is the limit of the sequence, say L1, it implies that this is true. This holds, rather, whenever we have this condition. So take note here, as x approaches x sub 0. So whenever x minus x sub 0 is less than delta. So for every epsilon, there exists delta with this condition. And then, if again the limit is L sub 2, we have this condition. And then this is true. Now, as you noticed here, we made this one epsilon over 2. In our definition, we only have here epsilon. We have our goal why we use epsilon over 2 here. Anyway, it doesn't matter because epsilon could be very small. It could be very small number, positive number. So it doesn't matter if we divide it by 2 because as long as this is a positive number. So that's it. Now, let's have here let's have this one, the absolute value of L1 minus L2. So again, because we want to show that L1 and L2 are equal, so we will show this one, and then our goal is to make this 0. Thus, the difference of the two limits is 0 to make them equal. So let's have this one. Notice that they are equal. We have just added and subtracted f of x. And then by using the absolute value property, this one, the first one is less than this one. We separated the absolute value. And then again, using the property, we just, factor out -1 in this one. So factor out -1, we have f of x minus L1. This is L1 here. Then we just copied this one. And then we separate the absolute value. This is -1, the absolute value of -1, and then the absolute value of this. They're just equal. Plus, okay, just copy this one. So here, we know that the absolute value of -1 is +1. So they're just the same. Plus, this will copy. And, of course, this one, the absolute value of f of x minus L1, by using the definition of the limit of a function, this is less than epsilon over 2 as discussed a while ago. Then this is epsilon over 2, so the sum is equal to epsilon. Hence, we have this one. The difference, the absolute value of the difference of the two limits is less than epsilon. So we note that the absolute value is always greater than or equal to 0. And, of course, from our result, we have here that the absolute value of the difference of the two limits is less than epsilon. Now, take note, in this case, we mean that the difference is less than any positive number epsilon. This is positive number. However, this is very small. So we are forced to, this is very small, and this one is greater than or equal to 0. So we are forced to make this 0, this one. This makes 0. Thus, we have this result. And so, we have shown that the two limits are equal. So, L1 equals L2. Therefore, the limit of the function is unique. Now, to illustrate more about the concepts of convergent or divergent sequence, let me illustrate some examples. So, first example, let us have this sequence here with a constant 2. Constant sequence. This is called constant sequence. So we will test if, or we will show if this is convergent or not by using the concept of a limit. So we will try to look at what is the limit of this constant sequence. Now recall that for the limit of a function or sequence, we will let epsilon greater than 0. So epsilon is a positive number. And then we will try to get the open interval. Open interval, and then we will try to look at if this open interval here, ito, contains infinitely many terms of the sequence. So as you can see, by the way, let me have this illustration here. If we consider this sequence, the constant sequence, so let's have, recall that for the limit of sequence, say for example, say L is equal to the limit of the sequence, limit of say sequence u sub n, as n approaches infinity, that one, if and only if, let's try to recall, for all epsilon greater than 0, we have these two conditions. First, the interval L minus epsilon to L plus epsilon contains infinite many points of, or many terms of the sequence. Whereas in the complement of this open interval, negative L minus epsilon, and this is closed L plus epsilon to positive infinity. This only contains finite number of terms in the sequence. Now let's try to use the real number line. Let's try to look at this. Obviously, we have here 2. First term is 2. Here, let's have the open interval. Let's have here 2. Let's test if 2 is the limit. 2 minus epsilon plus. This is 2 minus epsilon. So we will try to show that in this open interval, it contains infinitely many terms of the sequence, and then in the other side contains finite terms of the sequence. Now notice that our sequence is constant, so we only have 2 as the number in the sequence. The first term is 2, second term is 2, third term is 2, and so on. So in that case, this open interval here contains infinitely many terms of the sequence. And the other way, the opposite, the complement of it, we know that it has no term in the sequence, and we know that an empty set is finite, right? Empty set is finite. So finite lang siya. Therefore, this satisfies the definition of our limit of the sequence. We can say that the limit of the constant sequence, this one, say for example, let's denote this as u sub n, the sequence here. So the limit of u sub n as n approaches infinity is equal to 2. Since there is a limit of this sequence, therefore this sequence is convergent. So u sub n is convergent. Okay. Now let's have another example. Let's have this sequence here. So let's consider the sequence t sub n. We have this 1 over n, where n is a natural number. Actually, in my previous video, I have shown there that the limit of this is 0. So since there is a limit, therefore we can say that this sequence is convergent, and hence it converges to 0. Now let's have another example here. Given this sequence, we have this 1, negative 1, 1, negative 1, and so on. Now we will use the definition of the limit. Recall that if we let this as our open interval, this is 1 plus epsilon, 1 minus epsilon. This open interval here contains infinitely many terms of the sequence 1. And the same thing with this one, right? Now, let's try to use the definition of the limit of the sequence. If this contains infinitely many terms, in this open interval, the complement of it must contain finite number of terms. However, in this case, its complement also contains infinitely many terms of the sequence. Hence, the second condition is not satisfied. Therefore, we can say that the limit does not exist. So, since the limit does not exist in this case, we can say that this sequence is not convergent. Hence, this sequence is divergent. So that's it. Now, I hope you have learned a lot in this lecture. Now, in my next video, I'm going to discuss their Cauchy sequence. And let us see if there is a connection or relationship between convergent and Cauchy sequences. So that's it.